Hi everyone, welcome back. In this video we'll discuss buffer effectiveness and also buffering capacity. So when you're creating a buffer, the relative amounts of the weak acid and its conjugate base are really important. It's most effective when the concentrations of weak acid and its conjugate base are equal. So you've seen in the previous videos, in many cases, like the acetic acid was 0.1 molar as well as the sodium acetate was 0.1 molar. So it's more effective when you create a buffer that has equal concentrations of weak acid and conjugate base so that it can withstand additions of acid and base. So concentrations should not differ more than a factor of 10. So when it comes to calculating concentrations or deciding which concentrations of weak acid and conjugate base to use, it's most effective when the concentrations of weak acid and conjugate base are high. So for example, having a 1 molar acetic acid and 1 molar sodium acetate solution would be more effective than a 0.1 molar acetic acid, 0.1 molar sodium acetate buffer. There's just more acetic acid to, neutralize any added base and just more sodium acetate as well to neutralize any added acid. So it should make sense that the more concentrated the weak acid and conjugate base are, the better the buffer. In addition, when selecting a buffer for whatever research application you're doing, then the effective range for a buffering system is 1 pH unit on either side of the pKa of that buffer. So, in summary, you want to create a buffer that has approximately equal concentrations of the weak acid and its conjugate base. You want to make sure that the concentrations are relatively high, like 1 molar, for example, versus 0.01 molar. And an effective range for a buffering system is 1 pH unit on either side of the weak acid's pKa. All right, so let's do a learning check together. Which acid would you choose to combine with its conjugate base, sodium salt? So for example, acetic acid and sodium acetate is the sodium salt with the conjugate base, to make a solution that is buffered at pH 4.25. So looking at the answer choices here, which one would you choose? Hopefully you would choose C, right? So first things first is to make note, are you working with weak acids or a strong acid? So the first one is a weak acid, so that's great. And its conjugate base would look like this, right? And if you purchase the sodium salt, it would look like sodium ClO2. Nitrous acid is also a weak acid, so it's like, all right. And then its conjugate base would be the nitrite anion. You'd purchase it as sodium nitrite. And we have a weak acid here as well. We're looking at formic acid, and then formate, you would purchase that as sodium formate. And HCl is a strong acid. Remember, to create a buffer, you need a weak acid and its conjugate base. So this one immediately you should have crossed out and said, no, that's not going to even be good for a buffering system here. So then you were narrowed down to choices A, B, and C. And you'd want to choose choice C because we're trying to create a buffer that has a pH of 4.25, whatever application we are doing. And so you want to make sure the pKa of the weak acid in your buffering system is as close to the pH or the desired pH as possible. So in this case here, it was formic acid with the pKa of 3.74. All right, so now we know how to create a buffer and, some things to consider in making a good buffer. But buffers have their limits. You can destroy a buffer. It's not always going to keep neutralizing added acid or base. You can break it, and this is called the buffering capacity. So the buffering capacity is the amount of acid or base we can add to a buffer without causing a large change in pH. Remember, the whole goal for the buffer is to neutralize added acid or base, to try to maintain that pH as close as possible to what you've started with. But sometimes maybe you add too much base or you've added too much acid. And then when you see a drastic change in pH, then you have reached the buffering capacity. You've, exceeded it, in fact. So let's do an example together. Let's say we have a 500 milliliter buffer solution and it's 0.100 molar nitrous acid and 0.100 molar potassium nitrite. Determine whether adding 5 grams of hydrochloric acid will exceed the capacity of the buffer. And let's just assume that no changes or very negligible changes in the volume to make the math a little bit easier. Okay, remember when calculating the pH of a buffer after adding acid or base, we need to first do a what kind of table? Right, we need to do a BA table. So that allows us to determine, how the acid is reacting with our buffer and what's left over in our beaker, right? And when we do the BA table, we must work in what units? In moles. Fantastic. So first things first, I'm going to figure out how many moles of nitrous acid we have and of the nitrite, the conjugate base. So we have 0.100 molar nitrous acid And actually, let me make this look a little bit nicer so you can see the units cancel out. So moles over liters, that's molarity. I'm going to multiply it by 0.500. Technically it's 4 sig figs, so 0 liters. And so liters cancels out. So we have 0.05 moles of the nitrous acid because we also had 0.1 molar of potassium nitrate. We also have 0.0500 moles of the nitrite. So basically taking that 0.1 molar, moles per liter, multiplying it by 0.5 liters, then you get the moles that you're going to have initially before the addition. So we are adding HCl, all right? HCl is a strong acid, so it donates what in solution? Protons, fantastic, in the form of hydronium ions, right? Which part of the buffer is it going to react with? Is it going to react with the nitrous acid or the nitrite? Good. Hopefully you all said the potassium nitrite or the base, right? It's going to want to react with the base. Acids react with bases. Two acids are not going to want to have anything to do with one another, right? Okay, so let's write down the equation. I'm going to just write down the nitrite. Potassium is just a spectator ion. I like to write the net ionic equation. So that's my base. And then speaking of net ionic equations, HCl dissociates in the presence of water into the hydronium ion and the chloride anion, which the chloride is also a spectator. And so I'm just going to write down H3O, the hydronium ion, because that is the key component. This is what's dissociating and producing hydronium ions in solution. And that's what's going to be reacting with nitrite. So that's why I'm only going to be writing that down for the net ionic equation. All right, so nitrite gains a proton. It's our proton acceptor. So we have nitrous acid. And the hydronium ion lost a proton, so it turns into the conjugate base of hydronium, which is water. All right, once again, very important that you can predict these reactions. Talk yourself through it, like what's my base? What's the definition of a base? What's my acid? What's the definition of an acid? You're just transferring one proton at a time. All right, so before addition, we have calculated that we have 0.0500 moles of nitrite and also 0.0500 moles of the nitrous acid. The hydronium ion in solution is negligible, so we'll just write 0 before addition. Now, the first letter in our BA table stands for addition. What are we adding to our beaker? We are adding acid. We have to work in moles, and so you will need to convert 5 grams of HCl into moles of HCl. The molar mass of HCl is 36.46 grams per mole, and so when you do that calculation, you are adding 0.137 moles of the acid in solution. Everything is 1-to-1 here, and we know that the acid will react with this base. But we always have to ask ourselves when we're looking at this BA table is, what's my limiting reactant? And that's the one with the fewer moles here. Our limiting reactant is actually the nitrite. That's part of our buffering system here. And you're not going to subtract out 0.137 because you do not have 0.137 moles to start with. But it will completely consume your nitrite. So what you will write in here is saying, okay, I'm going to lose that 0.0500 moles. And as that acid is reacting with the base. It's creating the conjugate acid at the same time in your beaker. And so in this case here, we are creating 0.0500 moles of this conjugate acid as the nitrite is being consumed. Okay, so we want to figure out what we have after the addition. So the second letter A in the BA table is after addition. Because nitrite was our limiting reactant, we have 0 moles of our conjugate base left over. Remember that the acid from the strong acid here, the HCl, we added 0.137 moles. Some of that was consumed. Some of that reacted with the NO2 minus. And so what you need to do is take that 0.137 and subtract out 0.05 moles that was reacted to figure out what is left over. In this case here, it is 0.087 moles. Now with the nitrous acid, we started with 0.05, we made 0.05, so you have 0.100 moles. And we don't worry about water here. Okay, so let me review over that again. Because remember, the BA table is condensing a bunch of stoichiometry into one nice looking table here. But I want to make sure that you're following along. Okay, so we've added acid, HCl, into our buffer. It's going to react with the conjugate base of our buffer, right? We started with 0.05 moles, but when we added 0.137 moles, it consumed our conjugate base completely. It was the limiting reactant. And the limiting reactant is completely consumed here. Now, because when we added the acid here, some of it reacted, 0.05 moles reacted, everything's a 1-to-1 ratio here. Then I took that 0.137 that was added and subtracted out what was reacted, 0.05, and you get 0.087 moles of that strong acid left over in solution. In addition, as you're making this, as you're reacting your conjugate base with the strong acid, you're creating more of the conjugate acid in solution. And so as this was consumed, we were creating that same amount. Once again, 1-to-1 ratio, 0.05 moles of nitrous acid. So when you add that together, in your beaker, you have 0.1 moles of the nitrous acid left over. All right, so our question we always ask ourselves after the BA table, what's in my beaker? Because our goal is to figure out, is adding this HCl going to exceed the capacity of the buffer? Basically, we want to know what's the pH now after we added all this acid to it. What's in my beaker? Well, let's highlight it. We have the strong acid. We also have the weak acid. So what's left in your beaker is a mixture of acids. We have a strong acid, and in an earlier chapter, we had studied together how to calculate the pH when you have a mixture of acids. And we determined that if we have a strong acid and a weak acid, the pH of the system is determined by the strong acid. Remember, the strong acid's donating its protons. It's completely ionizing. So it's flooding it with all the hydronium ions, which suppresses the equilibrium of the weak acid based on Le Chatelier's principle, right? And so we don't even have to worry about the contribution of hydronium ions from the weak acid because the strong acid dominates, okay? Now, to figure out the pH based on the strong acid, we need the molarity. And so therefore, we will take that 0.087 moles, and the total volume we will assume is still 0.5 liters. that's 0.174 molar. This is equal to the hydronium ion concentration after the addition. The pH is equal to the negative log of 0.174. That is 0.759. That's extremely acidic. How do you know if we exceeded the buffering capacity? Well, let's calculate the pH of the buffer in pure water before addition. I'm going to use the Henderson-Hasselbalch. pH is equal to the pKa, or negative log of the Ka. The Ka for nitrous acid is 7.2 times 10 to the negative fourth, plus the log of the conjugate base over the weak acid. Remember, this is in pure water. This is before addition. The pH of this buffer in pure water would have been 3.14. So the fact that after adding 5 grams of HCl, the pH is changed to 0.759, I would say we definitely exceeded the buffering capacity, right? In order to not exceed the buffering capacity, what you add needs to be the limiting reactant. So if you're adding acid, this needs to be less moles than what you start with. If you're adding a strong base, same. You need to make sure that that's the limiting reactant, that you don't exceed that, because otherwise you're going to be left with strong acid in solution. Or if you're adding strong base, you're going to be left with strong base, which is going to change the pH of the buffer drastically. All right, thank you all for watching, and I will see you next time.